So let us show in this video that the set of even integers is equal in size to the set of the integers themselves. And in order to do that, I'm going to have to find some sort of a function that will become eventually a one-to-one correspondence from one of the sets into the other set. And therefore, it will basically say, according to what we know from the boxes and the definitions on this page, that the two sets have the same cardinality. Okay, so this function that I'm going to do is going to be called f of x. So in this case, I'm going to say let the function f be the function that goes from the set of even integers into the set of regular integers. And I want to describe the function f of x in this way. The function f of x takes the number that you start with and divides it by 2. Now remember, the number that you're starting with is a number that is even. So this function is good to go. It's dividing an even number by 2, which is fine. We can divide even numbers by 2. So the function f of x is going to be 1 to 1 and onto, and I'll have to convince you of that. So proof 1, that is 1 to 1. So proof 1, show that f of x is 1 to 1. So f of x is 1 to 1 because of the following. Let two numbers be from the codomain. So let y1 and y2 come from the codomain, which in this case is z, which is that z right there. And I want to choose them in such a way where they are equal. So then what will I know about those two guys? Well, y1 is the image of some x1. So in other terms, y1 came from mapping some x using the function f into the second set. And similarly, the y2 came from some pre-image. So x2 gets mapped by the function f into the second set, and it gives me the y2. So basically what I'm saying is that this y1 is the same thing as the f of x1, and I'm saying that the y2 is the same thing as the f of x2. However, f of x1 itself is really, in reality, just the x1 divided by 2. That's what the function does, right? According to the definition that I decided, the function divides by 2, the number that you put in. And then similarly, the number gets divided by 2 on the other side. So, in other terms, if I multiply by 2 on both sides, I get x1 equal to x2. So assuming that the two y1 and the y2 are equal, leads me always to believing that x1 and x2 are equal. So this proves that the function is 1 to 1. So this shows that the f of x is 1 to 1. But this is not enough, because now we need to prove that the function is also onto. Okay, so how do we do that? So I'm going to start on the next page, proof 2. How do we show that the function is onto? What do we have to do? Well, in order to show that the function is onto, what I have to do is grab an element from the codomain. So let the y1 in this case be from the codomain again. And I want to be able to convince you what the pre-image of it is. So I want to figure out what the number that maps to this y1 is going to be. Then its pre-image, the pre-image of y1 is y1 times 2. Okay, how do I know this? So in other terms, what am I saying? So in other terms, I am saying that if I take the 2y1 and plug it into the function f, I'm going to get at the end y1. That's what this sentence means. Okay, let's check. Is that really true? What does the function f of x do in general? Okay, so recall, here's what the f of x does. So recall means remember. The f of x basically takes your number that you put in and divides it by 2. So what would happen if I plugged in, instead of the x, the 2y1? So what would happen if I plugged in the 2y1 value? Okay, so that's supposed to be my input. If I plugged it in, it would get divided by 2 automatically, because the function always takes the number that you plugged in and divides it by 2. And when you divide it by 2, you get y1 back. And y1 that you got back is the number in the codomain. So that means you started with the number in the codomain and you found its pre-image. And you can do that for any random number in the codomain. You can always find the pre-image. Since it's doable for every single one of them, this shows that the function is now onto. So this shows that the function f of x is onto. And that's the QED of proof 2. Now, since the f of x function is 1-to-1, and also at the same time it is onto, comma, then we can say that the function f of x is bijective. Or in other terms, we can say that the function is a 1-to-1 correspondence. Okay, and why is that important? It is important because that means the sets that we started with are equal. Since the f goes from 2z all the way to z, this implies that the cardinality of 2z is equal to the cardinality of z, which is what we needed to show. So since we were able to find a 1-to-1 correspondence going from the first set 2z to the second set z, then that means that the sets are equal in size. That's what we wanted to prove, and so therefore we are finished. So if you think about it, this is kind of crazy because we're saying that there are as many even numbers as there are integers in the first place. So there are as many even integers as there are integers also. We can also do the same thing with the odd integers. We can show that the odd integers, there are as many of them as there are even integers, and together there are as many of those as there are integers, which is weird because supposedly the even integers is a subset of the integers. But remember, these are infinite sets that we're talking about. So the size gets kind of like, weird when you're talking about infinite sets.